All right, video number 6. What we want to be able to do here is take a look at graphing sinusoids and looking at even and odd functions. First of all, when we talk about even and odd functions, we're talking about the symmetry of a graph. So an even function is going to be symmetric across the y-axis, which means if we had an even function that started here and looked like this, that would mean on the left side of the y-axis, the same thing would happen. It would start here and have that same hump to it. Of course, if we're just looking at the graph and we see this, we might think that it's even, but we don't know what's happening elsewhere on the graph, so maybe something weird happens. How we can test to make sure a function is even is to look at what happens when we plug in the opposite of any x value. All right, so if I had some x value here, then this is going to be the y coordinate f of x. Okay? Now if I were to take the opposite of x, I would go just as far in the other direction, but we should have a same value on top. So f of negative x should be the same as f of x. This is where f of negative x would be, and it should be at the same spot. Odd functions describe rotational symmetry about the origin. So if that would mean that we would have to cross the origin at some point if we were to have that sort of a curve to it. If we rotated that around, we should end up with something like this. This is what we mean by symmetry about the origin, that it's a rotational kind of symmetry. So if x is right here, giving us an f of x value up here, that if we were to rotate that around, when we're talking about negative x, where would f of negative x be? Well, it should be just as far down as f of x was up. So our test is to look at f of negative x, and what we should get out is the opposite of f of x. Right here I have two functions, an even function and an odd function. I'm sure that if you kind of look closely and had to guess, you would probably guess correctly which one's even and which one's odd. But I want to use them to go through the process of how do we verify that something is even or odd. And it comes down to plugging in negative x. So taking a look at f of negative x. If I were to plug that in, I have 1/2 x to the third, and instead of x, I'll use negative x. Now, negative x to the third is going to be negative x to the third. And when I take that negative 1/2 times the negative x to the third, I have a positive 1/2 x to the third. Next, compare. Compare your answer you got of f of negative x to what we started with, the f of x. Are they the same? Are they opposite? All right, when we look at them, 1/2 x to the third is not equal to negative 1/2 x to the third. All right? But it is the opposite of that. So we could say that f of negative x is equal to the opposite of f of x, which would mean f of x is odd. Now, one point of emphasis that I saw at the summer conference for AP Calc this year is that they want to emphasize that if you're going to use a theorem or something like that, you have to identify the first part of it. You can't just use the result, but you have to use that condition as well. So going through this much work and then jumping down to saying f is odd is not really enough. You would need to also identify this part of it, saying that f of negative x is equal to the opposite of f of x. Therefore, f of x is odd. Let's go through that same process with g of x. If we're looking at g of x, I mean all those powers are even. The only odd thing I have here is this constant, so maybe it's neither, but I'm kind of leaning towards it being even. The only way to find out is to look at g of negative x. All right? So everywhere that there's an x, we're going to substitute negative x. And then simplify. When I take negative x to the fourth power, I'm left with x to the fourth. And negative x squared is x squared. Once it's all simplified, compare what we got as a result to what we started with. Are they the same? Well, yeah, they are. We see that g of negative x is equal to g of x, which means g of x is even. Speaking of graphs, we should look at the graphs of sines and cosines. Those are called sinusoids. This should be a refresher for you, but when it comes to sines, we can find a bunch of values for sine, but remember that sine starts at the origin, right, and goes up to 1, back to the origin, down to -1, back to the origin. And it repeats itself. So as we move backwards, we're going to continue with this wave. Right? And we get this nice little curve that looks like this. Right? It's periodic. It's going to repeat itself forever and ever. We can see that then the domain must be all real numbers. And when it comes to the range, we're only wavering between -1 and +1. So that y is between -1 and +1, and we can include both of those. Now, some other things about this, that when we look at one wavelength, so starting here and there, that's what we call one period of the curve. All right, one period of the curve has a length of 2 pi, which means that if we started at 0, of course we're going to end at 2 pi. Our most important points, like our turning points and stuff, happen at the marks that are labeled. Pi is halfway in between. This is pi over 2 and 3 pi over 2. And as we work negatively, each mark is at -pi over 2, -pi, -3 pi over 2, and -2 pi. So that we can see 2 complete periods of this curve. When we're talking about the center line, what I'm talking about is what's the line that contains all of those? It runs right through the middle. It is a line, and so anytime I ask you this, I'm going to ask for the equation of a center line. So it should be an equation. It's a horizontal line, so y equals, and that line runs through all the zeros. When we're talking about amplitude, amplitude is the height of one wave. And so since our middle is at 0 and our peak is at 1, we say our amplitude is 1. And when it comes to phase shift is talking about where we start. And in our most basic parent graph of y equals sine of x, our phase shift is going to be 0. You could maybe think of it as being at one of these other starting points, but we like to look at the middle of the curve. And one last thing is when we look at the symmetry of this curve, it is a rotational symmetry about the origin, which means that sine is an odd function. When it comes to cosine, there are a lot of similarities. It's just that cosine doesn't start at the origin. It starts up top at 1. But the curve otherwise looks the same. That it's periodic, so it's going to repeat itself, and it's going to have that familiar wave pattern to it. Because it continues, it's also called periodic. It has a domain of all real numbers because it's going to go left and right forever, and its range is also from -1 to 1 inclusive, that it bounces between +1 and -1. Also, its period is going to be the same. That when we look at one wavelength, because cosine starts on top and goes down like this, there's one wavelength. So we're going to start at 0, and its period will also be 2 pi, that one trip around the circle. So we label it the same way as pi over 2, pi, 3 pi over 2, and in the negative direction, same thing. Negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. When it comes to all the other descriptions, they're the same as well. That the center line is still y equals 0, because with this parent graph, it's centered along the x-axis. Its amplitude, the wavelength, or the height of the wave, is still 1, and its phase shift is also still 0 because cosine starts on top, not at the origin. When we take a look at its symmetry, there's a symmetry across the y-axis, which makes this an even function. I want to run through this as a quick reminder of what all the numbers in the equation are and how they affect different characteristics of our sine curve. So any number that's being added outside of the sine function, that's going to affect the center line. That means that our center line is at y equals 1. Whatever we're multiplying the sine by, that is going to be our amplitude. All right? That instead of just having sine, we're multiplying it by 2. That means that every sine value got twice as big. The period of sine is 2 pi. In this case, it's going to stay 2 pi. The only way it would change is if we took this entire difference here and multiplied it by some constant. Then the period would be 2 pi divided by c. Right? But in this case, we're not multiplying that by anything, so our period stays 2 pi. And finally, the phase shift. What's going to make this thing get back to being 0? Well, positive pi over 6 would be where that happens. So now if we're going to graph that, I kind of start at the bottom here with phase shift. Our phase shift is at pi over 6. And no matter what the curve is, we have 4 important points that we got to find after it. So 1, 2, 3, 4, and before it. And go the same distance. 1, 2, 3, 4. That is the one wavelength, those 4 steps. That means to get from the beginning to the end, we have to go 2 pi units. So if I were to add 2 pi to pi over 6, that would be 13 pi over 6. I also want you to identify all the steps in between. Now notice that there's 4 steps, so if I were to take this and divide it by 4, that leaves me with pi over 2, or 3 pi over 6. So I'm going to continue to add 3 pi over 6 to this 1 pi over 6. So 1 plus 3 is 4, plus 3 is 7, plus 3 is 10, and then plus 3 would bring us at 13. And of course, we should simplify our fractions right here and here as being 2/3 pi and 5/3 pi. Going the other way, we have to start at that 1 pi and start subtracting pi over 2. So 3 pi over 6, that would leave us with negative 2 pi over 6. Minus 3 is negative 5 pi over 6. Minus 3 is negative 8 pi over 6. And minus 3 is negative 11 pi over 6. Of course, go back and simplify our fractions wherever we can. Negative 2 pi over 6 is negative pi over 3. And negative 8 pi over 6 is negative 4 pi over 3. So now we have a very well labeled x-axis. Next, the center line is at y equals 1. So if I were to go here at 1 and kind of draw this dotted line, that's where our center is going to be. From there, we're going to use our amplitude to go up and down. Our amplitude is 2 units, so I'm going to go up 2 and down 2, so down to negative 1. And what we've just kind of done here is we've created kind of maximums and minimums. All right, so our curve shouldn't go bigger than 3 or less than this -1. Right? So that when we start graphing it, remember we're going to start with our phase shift at pi/6, and sine starts in the middle and goes up. So at each mark, I'm going to go to the maximum, back to the middle, to the minimum, back to the middle, back to that center line. And work same way the other direction. Right now I have this part of the curve. I need to repeat that going the other way. So go down to the bottom, middle, top, middle. Right? Notice that I'm not making sure that I hit y-intercepts or x-intercepts because my focus is on that center line and the maximum and minimum. But that's how we would use the transformations to graph that sinusoid. I know that was quick, so make sure that you ask questions in class about how to do that sort of thing.